So that velocity depends on head, diameter. Okay, so d may be the diameter, h is the head, g is the gravitational force, and also it depends on viscosity of the fluid mu and density of the fluid, and also one small v is there. Okay, so that v again it is dependent on the velocity itself. So whether it is uh, dependent like that or no, we need to check by this dimensional analysis. So now taking these all values, so they have mentioned where h is the head causing flow, d is the diameter of orifice. Orifice diameter is capital D, not the pipe diameter. Mu is the coefficient of viscosity, rho is mass density, g is acceleration due to gravity. So now recall the Buckingham pi theorem once again here. There we discussed about considering number of variables and number of fundamental quantities. So here total number of variables, if you recall, we have total how many variables are there? We have head, diameter, viscosity, density, gravity. All are dependent on velocity of the given flow. Okay, so total variables present here are dependent or independent. All together, if you consider, that is around 6. So total 6 variables are there. Okay. Now after that, once the variables are known to us, then we need to find out the fundamental quantities. How many fundamental quantities are required to represent these variables? So as you know, the dimensions of all these variables from the properties of fluid and other concepts studied in the fluid mechanics until now. So from that, I'm going to recall the dimensions as well as fundamental quantities. From that, we are going to list how many number of fundamental quantities are required to represent all these variables. So velocity is meter per second. I can write LT raised to minus 1. Head is in meter. I'll write in length L. Then diameter is represented by in meters. So again, it is L. Mu is viscosity of the fluid. What is the viscosity unit? So that you can recall here, and you can write ml raised to minus 1, t raised to minus 1. Density of the fluid, everyone know the unit. So I can write m l raised to minus 3. Then gravitational force, lt raised to minus 2. So once you recall all these dimensions, fundamental quantities, now I can just observe how many fundamental quantities are required to represent these variables. So I need m, I need L, I have taken, and T. So here we have not taken temperature or any other fundamental quantities. So fundamental quantities required here are 3. So m I will take 3, n I will take 6, and I will take the difference. So this difference between number of variables and fundamental quantities, one can note down how many pi terms we have to write. So totally 3 is the difference. So we have to write 3 pi terms. Now to write the pi terms, there is a method to write the pi term. Each pi term should contain m plus n 1 terms. What is that m plus 1? M is the repeating variables. Okay. So 3, what is the quantity 3 we got? So I have to choose 3 repeating variables plus 1. 1 is what? Non-repeating variable. So from this above 6 variables, first we need to choose which are those repeating variables. And to choose the repeating variables, again I will recall the steps here. What we have done? We have to chosen 3 parameters depending upon the MLT. We need to represent by choosing any one dimensional property, any one flow property, and any one fluid property. You can see at the end, last 3 steps, if you observe ABC, these 3 terms we need to choose because we have only 3 pi terms. In that, 3 repeating variables we need to find out. So these are the 3 repeating variables I will choose. So while choosing, you can observe in this problem what is happening. We have the same unit for or same fundamental quantity for head and diameter. Okay, so either you can take head as a repeating variable or diameter as a repeating variable, left to you. Okay, any one you can choose as a repeating variable. If you choose any one, geometrical properties considered, then left out variable whatever is there, d or h, that you have to consider one of the pi term as m plus 1 without any powers. Similarly, I'll come to the flow property. Flow property, all you know, velocity is a flow property, correct? Then we have gravitational force, which is responsible for the flow of fluids. So either you can choose velocity or gravitational force. That is also a decision you have to take. Next repeating variable is, what is that? That is the fluid property, not the flow property. And just see here, fluid property we need to select, that is mass density already present in the problem. Viscosity is also present in the problem. Surface tension not given. So what I have to do now? See the units. Between velocity and gravity, I can choose velocity. Why? Because fundamental quantities, the powers or the number of fundamental quantities raised to powers is very less. LT raised to minus 1 is comparatively very simple than gravitational force, LT raised to minus 2. So I can choose V as a flow property, G as a non-repeating variable. Or even though if you want to take a challenge and you want to check, can I go by G as a repeating variable and V as a non-repeating? That also you can choose as it is done in the problem. Next is the fluid property. We were talking fluid property, that is the last type. That is density as well as viscosity. Both we have in this problem, mass density and viscosity. So already I have told you, consider with minimum number of fundamental quantities and the raised powers should be less. So comparing mu and density, you can choose mu also, not an issue, rho also, but comparing both these variables, rho is having very less number of fundamental quantities, okay, m l raised to minus 3, and comparing to powers, viscosity is having less powers. So either of these two, in many problems, you can make one rule. Better to choose rho as a quantity, repeating quantity, that is having less number of fundamental quantities. That's all. So like this, now in this problem, we have chosen head, gravity, and rho. That is geometrical property, flow property, and fluid property as three repeating variables raised to respective powers depending upon the equation number. Say for example, pi 1 is the equation number 1. So I can take h raised to a1, g raised to b1, rho raised to c1 into, so m plus 1, whatever I have told you, that one term, what extra we have to add is, or we have to multiply is, either velocity or diameter or the viscosity, which are the left out variables. Okay, so once you considered hg rho, we left with vd mu. So take vd mu with the pi terms. So pi 2 I can write it as h raised to a2, g raised to b2, rho raised to c2 into mu or into d. So like that we have written the pi 1, pi 2, pi 3 terms by choosing the repeating variables as per our convenience and non-repeating variables like v, d and mu. You can replace these things also, not an issue. That also finally you will get the same result. Even if you take the repeating variables as vd mu and non-repeating variables as hg rho. I hope the point is clear to everyone. So now considering these powers, because again we are going back to Rayleigh's method, because in the Buckingham pi theorem we are partly considering the Rayleigh's method procedure also. What is that? We are going to compare the powers, okay, on RHS and the LHS, same procedure. But whatever the pi 1, pi 2 terms are there, for them and this vd mu, whatever the non-repeating variables are there, those two variables should not be applied with the powers according to Buckingham method. So now we'll take the first term. So what is that first term? Pi 1 equal to h raised to a1, g raised to b1, rho raised to c1 into velocity. So now these quantities we have to write in fundamental quantities, that is MLT. Okay. After writing with respect to MLT, you have to write the power with a1, b1, c1. Rest all units, say for example velocity, that is LT raised to minus 1 raised to 0. or we should not consider that power. Then pi 1, what to write in pi 1? M naught, L naught, T naught without any powers. So same thing we have done here. M naught, L naught, T naught equal to H is head, L raised to A1. Then we have taken G, LT raised to minus 2 raised to B1 into density we have taken, that is MT raised to minus 3 kg per meter, kg per, what is that? Mass density. Yes, mass density ml raised to minus 3 as per our dimension chart, correct? So density, if you recall the units in fundamental quantities, mass density is rho kg per meter cube. So as I told you, kg you convert into newtons, or sorry, kg per meter cube. It should be ml raised to minus 3, not p. So I think here some printing mistake is there in the books. Okay. So that confusion you have to overcome. That is mt raised to minus 3. You have to replace with ml raised to minus 3 into velocity. Velocity is meter per second. That is lt raised to minus 1. Okay. Please make the corrections with respect to fundamental quantities. Next, now on the LHS with respect to mass m raised to naught, we have power 0. So I'll equate that power 0 equal to, on right hand side with respect to m, okay, with respect to m, we have C1. So I can write C1 equal to 0 with respect to powers of mass m. Next I'll take L. So with respect to powers of L, on the left hand side always we have 0. On the right hand side there are many L terms. Which are those? We have the power A1 with respect to L. We have B1. Then we have minus 3C1. Then last term we have plus 1 because L raised to 1. So in this equation I can substitute C as 0. But we don't know B1 and A1. So for that, finding B1 or A1, again consider one more equation, that is pi 3 term. In pi 3 term, or say for example same equation, I'll take last term, that is T. So LHS T raised to naught, so 0 I'll consider equal to, here on the RHS if you see, I have powers with T raised to minus 2 B1. So that I'll consider first. Minus 2 B1 is the power. Next power with respect to T is minus 3 C1. Sorry, it is ml raised to minus 3. So I'll neglect it. We left with LT raised to minus 1 last term. So that minus 1 I'll consider with minus 2 B1. Now from this B1 I can find out as minus half. Okay, 0 equal to minus 2 B1 minus 1. B1 I can find out as minus half. Now this B1 and C1 to substitute in the equation of L, or powers of L to substitute. Now I can find out 0 equal to A1 plus into bracket minus half, that is B1 value, minus 3 into 0, C1 is 0, plus 1. So finally I will get A1 as minus half. So C1 is 0, A1 is minus half, B1 is minus half. So whatever the minus values are there, that will go to the denominators. Whatever the values without any negative or positive sign is there, that will be in the numerator. Okay. So taking all these negative sign and the values. Now I will go back to the pi 1 equation. I'll write it as pi 1 equal to, now see the powers. What is the powers? H raised to A1 I have to write. So H A1 is how much? Minus half, I'll write H raised to minus half. Next is G raised to, sorry, 1 minute. Yes, G raised to B1. So what I'll do now? B1 is minus half, I'll write G raised to minus half. Then rho raised to C1 here. Last term if you see pi 1, rho is raised to power C1. So C1 is 0. I'll write rho raised to 0 into velocity V. So V is not raised to any power. I'll keep as it is. Now in this pi 1 term, I can write it as V in the numerator, rho in the numerator, but rho raised to 0 is neglected. So V divided by, now square root is taken because it is having raised to half. So whenever the powers are half, I can take square root, and it is minus. So whenever the powers are minus, I have to write it in denominators. So V divided by square root of GH. This is the equation which relates the pi1 term. Pi1 is V by square root of 2G1. Sorry, square root of GH. So now, until now we found out the pi1. Similarly, we are going to find out pi2 and pi3 terms. So I'll just directly go to the pi3 term. I'll tell the procedure. Now pi3 term I'll recall, that is h raised to a3, g raised to b3, rho raised to c3 into mu. So why I'm skipping pi2? Because you know d is L. You can compare the powers and you can write pi2 term as, so pi2 I can write it as directly d by h. We are getting d by h. Now we'll see the procedure for pi3 because mu is having many units, many fundamental quantities. So pi3 is h raised to a3, g raised to b3, rho raised to c3 into mu. So again, recall the pi term fundamental quantities, that is m0, l0, t0, equal to head is l raised to a3, then g is l raised to lt raised to minus 2. Please all of you observe the fundamental quantities are correctly taken or not. Gravitational force is, yes, anyone can tell me gravitational force, what is the fundamental quantity you have to write? Any response for gravitational force unit and fundamental quantities? Any connectivity issues there in between? Okay, now mlt raised to minus 2 is the unit. So how it is mlt raised to minus 2? What is the units, measuring units of gravitational force? Gravitational force we are taking meter per second square. Correct? So meter per second square means L raised to 1, T raised to minus 2. Okay. So on that basis, we are writing all these dimensional fundamental quantities. So that meter per second square is written as, at the last line you can see, LT raised to minus 2 raised to B3. Then rho raised to C3 is there. So density. So density fundamental quantities, if you recall, I can write it as ml raised to minus 3, correct? ml raised to minus 3 raised to C3 into mu, non-repeating variable without any powers. So without any powers means whatever the powers is there for the mu, only that you have to write. M L raised to minus 1, T raised to minus 1. You should not take D3. Okay. Now once you consider this MLT equations, LHS and RHS, now we are going to compare these powers. Okay. So 0 equal to, what is that 0 equal to with respect to M? If I talk for equation M, 0 equal to on LHS, 0 equal to C3, 1. So C3 plus 1. This is written here. Similarly for L, 0 equal to A3 plus B3 minus C3 minus 1. Here, A3 plus B3 minus C3 minus 1. Next is for T, time. So from pi3 term, 0 equal to, so focus on the powers of T. 0 equal to minus 2 b3 minus 1, minus 2 b3 minus 1. Now from this one can find out c3 and b3 first, because only one unknown and one equation is there, you can solve it. So c3 b3, once you find out c3 is how much we are getting, minus 1, b3 we are getting minus half, then a3 we are getting minus 3 by 2. Means what? All these repeating variables are in the denominator and non-repeating variable is on the numerator. So I'll write phi 3 equal to h raised to a3. What is a3 value? Minus 3 by 2. I have written g raised to b3. b3 is minus half. I'll write here. Then rho raised to c3. c3 is minus 1. So rho raised to minus 1 into mu. Now mu I'll keep in numerator divided by here. H raised to 3 by 2 kept as it is into rho, because it is minus 1 only in the denominator. G is minus half. You can write g raised to positive half in the denominator, or else you can take the square root of g. So like this, in the pi 3 term, the properties are related like this. So in this problem, for our reference, we have taken pi 3 term. If you take pi 1 term itself as like this, we will get same thing. If it is pi 1 term, okay, we will get mu by h raised to 3 by 2 rho into square root of g. So similarly, now what I'll do is, these all units I will now convert. So for simplification, what they have done? For simplification, they have done. Well, so for simplification, they have again divided this h term. What they have done? Square root of h into h they have taken, so that it will be h raised to 3 by 2. So mu divided by h rho into square root of 2gh they have taken. Now they have multiplied and divided by v. Okay, so these all things need not be done regularly, but what they have done in the question is, we need to prove it. Not only finding one equation, you can find out equation, you can skip it, but finally the problem only they have mentioned what to be found out. So the procedure of the solution also it will be helping us to find these related quantities, how to be written. Okay, so with respect to mu, if you see, it should be written like mu divided by rho vh. So here we don't have rho vh. So what they are doing? They are going to multiply with v. So mu divided by rho vh. Finally, we should get like that. So they are going to try it by multiplying and dividing v, or separating this h raised to 3 by 2 like square root of 2g and square root of h and h, like that they are trying. After trying, they found here what they found: mu divided by h rho v. They have separated one side, because in the question they are asking like this: mu divided by rho v h will they need. So they are writing like this: mu divided by rho v h. Now into what is the left out terms? V divided by square root of 2gh, not 2, square root of gh. So v divided by square root of 2gh, if you see, it will replace the pi 1 term. So they have taken pi 1 into mu divided by rho vh. Okay, so now they will take all pi 1, pi 2, pi 3 term. Now they are going to substitute in the v equation, how this v is related to remaining terms. So v equal to, see here, what is pi 1? Pi 1 is v divided by square root of gh. Okay, so that they have taken v divided by square root of gh equal to phi of phi of, what is phi of? Pi 2 term. Pi 2 term is d by h. Here, d by h. Pi 3 term is, finally we got it, mu by rho vh into pi 1. Like this we got here. Pi 1 into mu divided by rho v h. Now from this we need to find out v, correct? So whichever the equation is having in the numerator v, they have taken on left hand side, that is pi 1. So pi 1 equal to function of they are finding. Now they will replace all the terms to find only the v. So v equal to, see the replacements what they have done, v equal to square root of 2gh. Now can anyone tell me why they have taken 2 here, why they have not considered 2 here, or any problem is going to happen if I multiply 2 or 5 or 10 with respect to this square root of 2gh? Any answer from your side? Or recalling the earlier class, you can tell me, can I write square root of 2gh directly? But in the earlier step, we don't have 2. You can unmute and tell me. So why they have taken square root of 2gh? Because one thing you can tell me, it is asked in the question to prove like this. I have written, okay. One more thing is, by dimensional analysis, we have seen constant value you can multiply with the function of any term. So that constant value they have taken square root of 2. So constant value you can consider any value. See here, in any equation if you see, here I think pi 1, pi 2, pi 3, phi of. So anytime if you multiply with any constant, okay, the values are not going to change as per our dimensions are concerned. Dimensions are not going to change. Only the value is going to increase or decrease. But this constant value, if you multiply with any dimensions, it is not going to change the results. As here you can see Rayleigh method. Here they have taken k into L raised to minus 2. What is that k? K they have taken 2 pi, because everyone knows that for a pendulum, I can substitute k as 2 pi so that it is related to time 2 pi square root of L by g. Okay, so like this, if you know the constant, you can write 2 pi. If you don't know, you can keep k into square root of L by g. Similarly like that. Here also you can see. Power is directly related with respect to HWQ or HQW. Constant is a proportionality, or to tell that if any value is multiplied with the dimension, there is no change in the values or fundamental quantities. So that k is taken. And the problem question also, they are not told anything to prove. So whatever the result you get, you can keep as it is. Similarly here also, whatever the result is got, you can keep k into square root of L by g as it is. But in case if you know k value, you can substitute. So what they have done in this problem, k value they have told. That k value is square root of 2. So I am going to multiply square root of 2 into square root of gh, function of, so right hand side I am going to write now, d by h, comma, mu by rho v h. Okay, so it's like this. What they have done, they have proved that v depends on velocity of the flow, depends like this, by taking square root of 2gh into function of d by h, comma, mu by rho v h. Okay, so same thing we have derived here. So I think on the similar lines you can solve this problem also. So this I consider the last problem for the understanding of Buckingham pi theorem. Now at this moment I think the process is known to everyone. So I'll just
Sir,
yes,
so can you explain last step?
yes,
So can you explain last step? The
yeah,
last one.
okay, okay, one minute. Here,
Yes, sir.
yeah, pi 1, pi 2, pi 3 terms are found out. Pi 1 is V by square root of GH. Pi 2 is D by H. Then pi 3 they have found out mu by rho VH into pi 1. Okay. So now these all values they are going to substitute. That is, on the left hand side we can write pi 1 value V by square root of GH. Here pi 1. Pi 1 is V by square root of GH. Why we are writing on the left hand side? Because we want V value. Because in the problem only they are asking V, find V. If they don't ask, they will tell find V which depends on all these parameters. I can write directly. So I have taken left hand side V by square root of,
Excuse me, sir.
yes,
So whichever variable we want to have to write it on left side, right?
left hand side, yes.
Okay.
You can recall from the old problem. Here, the resistance are experienced by a partially submerged body depends upon. So that is required. That is a dependent variable. R is on the
Yes.
left hand side, like that. So similarly here directly they have given V on left hand side. Even if they don't give, they will tell in the question. Find V or velocity depends on these all parameters, like that they will tell. Then you have to take V on the left hand side. So they have taken V on the left hand side, V by square root GH equal to function of. So function of D by H, correct? Again you can take pi 1 term there, pi 1 into mu by rho VH. But here what we need to show is, finally, actual value if you want to find out for V, you can multiply with pi 1. But in the problem they are asking that whether it is dependent like this or not, that we need to prove. So it is dependent like that. So what we are writing, D by H, okay, and also it is dependent on mu by rho VH. Pi 1 is kept as it is. Why? Because we don't want that term in the substitution. Okay, so here now if I take only V on the left hand side, I can multiply with one of the constant square root of 2gh as per the problem given. Then it is a function of d by h comma mu by rho vh. It is also a function of what is that pi 1 term. What is pi 1? Pi 1 is v by square root of gh. It is also dependent like that. Actually, we have to write like that. But as per the question, we need to write this much. Whether it is dependent like this or no. Yes, it is dependent like that. Still, if you want to write function of, you just multiply that mu by rho vh into pi 1 term. What is that pi 1? V by rho gh, square root of gh. Now it is clear?
Yes, sir.
Okay. So multiplying in the dimensional analysis, multiplying any constant on right hand side or left hand side will not change our dimensions. That you have to keep in mind. Value may be varying, but dimensions will not change. Yes, I think this problem will go shortly. Okay, before the break time, we'll complete this. And the next class will take the remaining syllabus. So again here, they're asking for the stating the Buckingham-Pi theorem. You can just recall the Buckingham-Pi theorem, what is the definition and other things from this theory. So already discussed. Then we have the efficiency of a fan. Okay, this type of problem we have not taken. We will solve this. Efficiency eta of a fan depends upon. Now all of you observe. Efficiency of the fan, that is eta, depends upon, means left hand side should be efficiency. That is the dependent variable. On which all parameters it is depend, how it is dependent, we have to find out. The parameters given are density of the air or water, rho is given, dynamic viscosity mu of the fluid, angular velocity omega, diameter d of the rotor, and the discharge. So here they have not mentioned any fluid because we are just focusing dimensions, not the quantities or the particular substance. So it is dependent on rho, mu, omega, diameter, and discharge. Total, it is dependent on 5 terms as like earlier problem. One more variable is efficiency. So totally 6 variables are there. So they have taken 6. Now in the question you can see express efficiency in terms of dimensionless parameters. This also very important. Until now didn't check these ratios d by h or square root of 2gh mu by rho vh, or here also we have not checked whether they are dimensionless or dimensional. Okay, but here what they are asking, efficiency you have to write in terms of dimensionless parameters. Why? Because efficiency also don't have any dimensions. And also what is the check we have to do? On the right hand side, whatever the equations you are going to write at the final step, combined together, if you multiply, divide, add, subtract, whatever you do, that should be a dimensionless number that you have to check. But definitely by Rayleigh's method or the Buckingham Pi theorem, we are going to get the same uh, dimensions on left hand side and right hand side. Okay, next. But what is the concern of dimensionless parameter? We'll see in this problem. So number of variables 6, dimensions you only write it rho mu omega is the new word here. Okay, so angular velocity we are not going to focus on other units because angle don't have any dimension. Angle is having only in radians or in other measurements it is shown, but as per the dimension we don't have the fundamental quantities for the angle. But angular velocity, if it is required, you can see here. Yes, it is a kinematic parameter because it is having per second value, velocity, angular acceleration, angular velocity omega. Radians per second. For radians or angle, we don't have any dimension. But per second, we have dimension that is t raised to minus 1. I hope it is clear. So t raised to minus 1 is the only for per second. So for radians or degrees or angle, we don't have any fundamental quantity. This you have to keep in mind. Yes. So taking all the variables, number of 6. Now I will see how many fundamental quantities are there. M is there throughout the equation, L is there, and T is there. So again 3. So 6 minus 3, we left with 3. So 3 pi terms we have to write with one extra term, that is M plus 1 variables. So pi 1 I will write now. Again go back to the steps of Buckingham Pi theorem. Choose any one geometrical quantity. So geometrical quantity means we have only diameter, nothing else. The length, whatever is shown, is the fundamental quantity. We have only the diameter. So diameter we have chosen one repeating variable. Next is the flow property you have to choose. What is that flow property? Velocity, acceleration, not given in the problem. Then left with per second, whatever the per second is there is the angular velocity is given. That is a kinematic property. So kinematic property we have chosen omega for pi 1, pi 2, pi 3, repeating variable. Next repeating variable, as I told, you can consider the fluid property. Discharge is also a flow property only. Now can you tell me, in between angular velocity and discharge, why I have chosen angular velocity only? Why not discharge? If you answer this type of question, over, you can solve any problem. Because discharge is also having per second here, kinematic or flow characteristic. But I have not chosen Q as a repeating variable. I have chosen
Because
only, yes.
so because of less fundamental terms.
Yes, fundamental quantity, if you see, L3 into L raised to 3 into T raised to minus 1, it is having 2 fundamental quantities and powers are high. But if you see the angular velocity, it is having only one fundamental quantity and raised to minus 1. So simple is angular velocity. That's why I have chosen omega. You can choose discharge also to find the result. Okay, if you want discharge, you can write Q here, Q raised to B1, Q raised to B2, Q raised to B3 also. But the process may be a little bit more. It may consume more time. Next is, out of the fluid properties, that is viscosity or mass density. Here also, as I told, in every problem rho is there, directly take it because it is having minimum fundamental quantities. Okay, ml raised to minus 3. So I have chosen rho C1, rho raised to C2, rho raised to C3, all pi 1, pi 2, pi 3 terms. Next, we left with remaining three non-repeating variables. You can add anywhere. So here it is added with efficiency, mu, and discharge. Or you can keep in mind that whatever is found out first, what to be found out from the problem, take it for the pi 1 term. That is efficiency. Next with mu, next with discharge. Okay. So now from pi 1, equating the powers, we found out, directly I'll tell, we found that from the pi 1 term, we left with without any dimensions. Okay. Only we left with efficiency term. Then pi 2, after finding pi 2 term, we left with mu divided by d square omega rho. Mu divided by d square into angular velocity into mass density. Next, from the pi 3 term, okay, pi 3 term, after equating the powers of m, l, and t separately, we found out C3 0, A3 minus 3, B3 as minus 1. From this, after substituting with all the repeating variables with powers found out A3, B3, and C3 powers, okay, into Q, we found out that pi 3 term is Q by d square into omega. So taking this pi 1 term efficiency, pi 2 term as mu by d square omega rho, pi 3 as Q by d square omega, after taking as a function, I will write efficiency equal to, why? Because we need to find out efficiency equal to function of pi 2 and pi 3. What is pi 2? Mu by d square omega p is written here. Next, pi 3 term is Q by d square omega, it is written here. Now in the question, they are not asking to prove the equation what is given. Equation is not given here. So whatever is found out, only that thing is kept here. Now to check whether it is dimensionless or not, because that check they have not done. See here. What is the check we have to do? Express the efficiency in terms of dimensionless parameters. Now if you want to find out dimensionless, take the dimensions of mu, fundamental quantities, and fundamental quantities of diameter, omega, and rho. It should be cancelled. All the dimensions should be cancelled with respect to numerator and denominator. It should be 0. Similarly for discharge. Discharge is L3 into t raised to minus 1. Okay, L3 t raised to minus 1 divided by, see here, d square is L square, omega is per second, t raised to minus 1. So if you consider that, altogether the dimension should be 0. Here also the efficiency dimensions, if you see, there is no dimensions for efficiency, 0, 0, 0. Okay, that check you have to make and you have to write. Finally, we got efficiency as a dimensionless property. Is that clear? So we'll have a break now. Again at 11, we'll start the class. Yes, we'll continue the class. Yes, shall we continue? Anyone to join the class? Okay. Yeah, next we need to discuss about our syllabus is having dimensionless numbers and its significance. What is the importance of that dimensionless numbers studied in the fluid mechanics? Then we are going to discuss about model and similitude later after this part. That is model analysis and similitude and its similarities. So this is the completion of our syllabus. Okay, so today we'll discuss all these remaining things and we'll complete the fourth module. Okay. So now coming to the dimensionless numbers. First thing is the equation what we are writing for the dimensionless numbers are not having any dimensions. So earlier I can take one example, that is Reynolds number represented by RE. So Reynolds shows that only by one number one can decide whether the flow is laminar, transitional or the turbulent flow, which is not having any dimensions. So such type of numbers are called as dimensionless numbers. This is one thing. Now what is the significance is, so just taking these numbers, one can decide what type of phenomena is happening with respect to fluids. That one can decide. Now coming to the required things or the required forces to find these dimensionless numbers are, one is the inertia force. So this inertia force due to its self mass is required to find out all these 5 dimensionless numbers. So below we have listed 5 dimensionless numbers. Okay, and to find these dimensionless numbers we need these 6 or 5 dimension numbers, or which are having some dimensions. Which are those? We need to use inertia force, viscous force due to viscosity, gravitational force of the fluid, pressure force and capillary force, and compressibility or the elastic force. So these 6 forces are required to find these 5 dimensionless numbers. In this, all these 5 dimensionless numbers need the inertia force. This is inertia force is common for all the dimensionless numbers. Why I'm telling this, to remember how to relate these two dimension numbers, and after taking ratios, how we are finding these dimensionless numbers. Okay, so now we'll check how to find these Reynolds number, then Frod's or Frodde number, then Euler's number. See, according to the pronunciation, this can be pronounced in any way. Okay, some books have pronounced like Frod's law or Frod's number. Some have pronounced like Frodde number or Frodd also. You can remember easily. You can recall it as Frodd also. Then next we have Weber's number, WE. Then we have Mach number. So generally Reynolds number you all know. We need the inertia force. Okay, and we are taking the ratio with respect to rho VD. Okay, so that rho VD, if you recall, we need the viscous force. So similarly, we have the Froude numbers. So for Froude number, we need gravitational force to be taken with ratio. So like this you can remember, because always if you see the gravitational force, any experiment if you do, anything if you do, we have to, or we should not forget this gravitational force. So Froude has introduced this gravitational force. That is also a Froude only. Okay, so if you take the ratio of inertia force to gravitational force, that is called as Froude number. So similarly, if you take the ratio of inertia force to the viscous force, from that we can find out Reynolds number. Similarly, for the Euler's number, what ratio you have to take now? You have to take the ratio of inertia force to the pressure force. That is the pressure force. Similarly, for the Weber's number, we need to take again same. For all the dimensionless numbers to remember, in the numerator you have to take inertia force, in the denominator you have to take a different force. So for Weber's number, we need surface tension force in the denominator. Then last is Mach number. This is also a very important component here in our future compressible flow discussions. So there we are taking ratio of inertia force to the elastic force. So we discuss one by one and we'll understand how this is a dimensionless number and what is the formula used. So first coming back to the Reynolds number. So Reynolds number is the ratio of inertia force to the viscous force. So now if you take the ratio, now and we have to prove it is a dimensionless. So inertia force is nothing but what? Mass into acceleration due to its own mass. So mass I can substitute it as density into velocity. Okay. Into this acceleration I can write it as change in velocity with respect to time. Okay, I hope you are understanding. So that value I am taking here. So now once you take these values, sorry, this mass is density into volume. Any body, if you consider, mass is density into volume. The acceleration is change in velocity per unit time. So this V and this V is different. Now substituting this volume as area into length, assuming a body is having linear dimensions, not the diametrical dimensions. I can write it as rho AL into V by T. Okay. Then I can rewrite it as in the fundamental quantities, I can substitute, or I can write velocity per unit time, okay, in terms of V by T itself, but area we are going to substitute as L square. What I told, assuming area is taken from the linear quantities, length into breadth or length into some length. If it is a square body, in such conditions I can take rho L square as area, L square as area into rho into L by T into velocity. So taking these all values, I can write the inertia force as rho V square into L square. Okay, so how this is V square? Velocity square. So per unit time, if the length is changing, okay, then I can call it as velocity also. That L by T itself, I can write it as velocity. Then they have written rho V square L square. Now in the viscosity or viscous force, all of you know that it is mu equal to tau into du by dy into area is equal to tau. So tau is the shear force or the viscous force. So that they have written here Fv, small v they have taken with F. So taking that tau equal to mu into du by dy here, okay, into area. So on what area it is acting with shear force, that is called as viscous force. So now considering this du by dy with full given dimensions, I can write it as change in velocity with respect to change in length, because y is changing in length. I can write it as v by L. Mu I'll keep as it is. Area I can write it as L square. Again assuming the area is taken with the linear dimensions. So I can write it as mu v L. So these two things are substituted like this so that we can take some ratio and we can write in simplified form. So now taking the Reynolds number, that is inertia force by viscous force, one can write it as rho v square L square by rho v L. Okay, now we can cancel, mu v L. So here you can cancel v and L in the denominator. Now finally we left with rho v L by mu. or already we have studied rho v d by mu. If it is circular dimensions, I can take hydraulic diameter as d. If it is a pipe, if the flow is taking place on a open channel or a surface, I can write it as L. Okay. So depending upon that, they have written rho v L by mu. So L you can write D or L. And rho by mu or mu by rho. You know one more quantity, that is what? Kinematic viscosity. That also you can write. So finally we are using many times this Reynolds number, which is a dimensionless number. So if you substitute the dimensions of rho, v, L and mu, we'll get Re as a number, not with the dimensions of the measuring quantities. So what is the significance? Now this is used in fluid flow problems where viscous forces alone are predominant. Where the viscous forces are acting and we need to find out with respect to viscous force what is the property of the fluid or what is the Reynolds number of the fluid, then we can go by Reynolds number. Okay. If the viscous force is of prime importance and the dynamic similarity is said to exist. So later we'll see what is this dynamic similarity. So again, same thing we are going to repeat in the similitude also. Dynamic similarity is said to exist between the model and a prototype. So as of now, you just remember a model is a small body which will resemble with respect to actual body. Say for example, one dam is constructed. Before constructing one actual dam, that's a prototype. Before making a prototype or an actual dam with actual conditions, before that, many times we go by the models. Small models are built with small scales. Then some experiments are done on the model. Then we are going to go for the actual model, that is called a prototype. So in between these two things, there should be three similarities. That is geometrical similarity, kinematic similarity, that is flow similarity, then the property similarity, that is the dynamic similarity. So in that, we are going to talk about dynamic similarity. So whenever dynamic similarity is considered, we need to focus on viscous force or the Reynolds number. Next is we measures the relative magnitude of the inertia force to the viscous force. To find how much is viscous force or how much is inertia force by ratio, one can also use this Reynolds number. If the values are very less, so that one can tell viscous force are very high, then the flow properties. Then whenever higher the Reynolds number, then what will happen? Inertia forces will be higher and flow will become turbulent. So like this, by using this Reynolds number, one can make many conclusions. Also, we discussed earlier that is below 2300 is separated as a laminar flow. If it is between 4000 and 2300, we are going to call it as transitional flow. And if it's more than 4000, we are going to call it as turbulent flow. So where this application you can see the Reynolds number application, that is in flows in incompressible flow. So whenever compressible flow are taking place with respect to air or gas, there we are not using this Reynolds number. We are using only in incompressible flows, that is in liquids, and it is in a closed pipe only. And wherever resistance is experienced by the submarines, aeroplanes, or fully submerged bodies, in such cases we are going to check the Reynolds number of the flow or the Reynolds number of the body which is moving with respect to stagnant water. So in such conditions, this Reynolds number is very important for us. So I hope already you have studied something about Reynolds number, and by this we understood what is the ratio of values are taken to write this equation. Is it clear to everyone? Reynolds number is understood or no? Okay, next one is the Proud's number. So Proud's number is the ratio of again inertia force to the gravitational force under root. So now again taking this inertia force as it is rho v square L square in terms of length, velocity and density. Gravitational force again we are converting into length density. So it is written as G equal to M into G. That is gravitational force, how much it is applied on the bodies. It is depending upon mass and gravitational force. So that can be written as mass can be substituted as rho into V into G. So taking this value, I am going to substitute. So volume again see here as like area L square. Then substitute volume into L cube. Here, you can see volume. You can substitute L cube directly here, and you can write inertia force. Okay. So here volume they have substituted directly L cube into G. So now Proud's number is nothing but square root of inertia force to the gravitational force. Reynolds number was without square root, it is ratio of inertia force to the viscous force. So other than Reynolds number, all other dimensionless numbers what we are studying in our syllabus, or whatever these 5 dimensionless numbers are studied, apart from Reynolds number, these all numbers you have to take square root of ratio. Okay. So that's why Proud's number is also taken under square root inertia force to the gravitational force. If you take, I'll get V divided by square root of Lg. That is after taking ratio of inertia force to the gravitational force. It's the ratio of velocity to square root of length into gravitational force. Now what is the significance of this Proud's number? The significance means one can remember this gravitational force. So wherever the fluids are flowing or stagnant, with respect to gravitational force, how it is behaving, to check that we are going to apply Proud's number. Okay, that is one thing. So if the gravitational force is of prime importance and dynamic similarity is said to exist between model and prototype, hence Proud's number of the model and prototype is same. So this is true for all the cases. If you check any similarities between model and prototype, these all dimensionless numbers should be similar. Okay, or for a given scale, it should be same. So applications are so flows with free surface effects or flow with the spillways flowing from the high head to low heads. Okay, that is one thing. And slow scales between the gates, spillways, open channels, how it is flowing. With respect to gravity, there we are going to discuss about Proud number. And also it is used where waves are likely to be formed. So waves are generally happening because of the gravitational force between moon and earth. So any gravitational force is changing continuously between moon and earth on the external surface of the earth and moon. So due to which what happens, the waves are going to form. Also, between only with respect to earth, if you see, because of the movement of earth itself, some waves are going to form. The waves are going to form depending upon different phases. Also, if you move a big body like a turbulent sea or a ship is moving in a stagnant water, there also some waves are going to form. So these waves are controlled by its gravitational force. To study those things, we are going to apply this Proud's number. Next is the Euler's number. Now, Euler's number, whenever it comes, you remember the pressure. Because Euler's is there in every aspect, like mathematics if you take, or fluid mechanics if you take, or any other subjects if you take. Many times you come across this Euler's name. Okay, so we have done very much work with lot of pressure. So you can take the ratio of under square root ratio of inertia force to the pressure force. So how the pressure force is written? Pressure is force per unit area. So that force due to pressure is pressure into area. On a given area, how much is the pressure acting? If you multiply those two things, I will get P into L square. The only thing you remember that all this area, volume, other things should be converted into linear dimension. So A is written as H square. Now taking ratio, I can write it as Euler's number is ratio of velocity to square root of v by rho. Then note down Reynolds number is rho v L by mu, rho v L by mu. Proust number is v by square root of Lg. Then Euler's number is v by square root of v by rho. Now where this is used, already you have seen the Euler's equation, Bernoulli's equation. You have studied about the uh, different heads due to pressure, due to kinetic forces, or kinetic head, and return head. So in such cases, how the pressure force is affecting the fluid flow or the fluid properties. In that case, we are going to use this pressure or the Euler's number. Okay. The other thing is, if the pressure force, again same thing, model and prototype, this Euler's number should satisfy. For a small scale given model, the Euler's number what you have found out should be proportional to the big prototype. The actual model what you are going to decide later and you actually run in the actual environment, it should match. So flow through closed pipes, because there also we have pressure. Discharge through orifice, ventimeter or pitot tube or sluice gates. Sluice gates are nothing but the open channels, where the gates are there and some pressure is applied on the gates, or submerged body we are seeing. Some surfaces are inside the water, and what is the pressure acting on the bodies. So those are called as sluice gates. Next is the water hammer. So whenever you close the gates, water will come and hit the gates. Or you can see the penstock of the turbine. The flow is closed. Once the flow is closed, also the water will come and hit the closed wall. That is called as water hammer. Or once you open this penstock, flow of water to the turbines, to the Pelton turbine or the Francis turbine, the water will come and to the moving gears. So there, to study this water hammer, there also exists the pressure force. So in such applications, we find this Euler's number. Okay. Next, you can note down Weber's number. So Weber's number is the ratio of inertia force to the surface tension force under square root. Okay. Whenever this name comes Weber, you can recall this surface tension. So Weber is having tension, Euler is having pressure. Okay. And we all have doubts. So Weber, I can take the ratio of under square root inertia force to the surface tension force. So once you take this surface tension, all of you know by this capillary action and droplet, you have studied this sigma surface tension into L for a given length. So because it is not acting on the area, it is acting on the boundary of the circle or a hemisphere or a sphere, or it is only acting on the boundary of the capillary tube. So that length is taken, all diameter is taken. Sigma into L is taken here. So Weber number, after taking this ratio, we will get V by square root of sigma by rho L. Okay. You can note down this equation. Weber number is given by V by square root of sigma L by rho L. So once you substitute all these fundamental quantities NLP in these ratios, we will get just a number without any dimensions. That's why it is a dimensionless number. Now why this is also important? To study the surface tension forces which are acting on the fluid surfaces. Okay. Applications are, as I told, capillary tube, thin sheets of fluid flowing over a surface or in a closed channel. Just the surface is flowing, then there will be some surface tension. Then the flow of blood in the veins. So here you have gone to outside engineering. They are recording some medical applications like flow of blood in veins, arteries, some capillary action is taking place. So depending upon the surface tension, how this flow is going to be controlled. So that example is also taken. So these are the applications of this reverse number. Last one is Mach number. Again, as I told, under square root, you have to take some ratio. Which ratio? Inertia force and elastic force. So Mach number here is very important to focus on. Mach number is considered for compressible fluid outside. Okay, majority of the case we are considering Mach number for the compressible fluids like gas and air. Okay, so here finally, if you take the elastic force of any body is the multiplication of bulk modulus into area. The bulk modulus is into K here. This is the bulk modulus. Area is substituted as square. Taking this ratio, we will get the reverse number, sorry, Mach number, should be Mach number, not reverse number. So just to cancel this reverse number, Mach number will get us E times rho is one of these, or to take this by rho square, the velocity of sound. To take the gas, consider what the ratio of velocity of the body with sound if you compare, that is called as very important for the particle fluid. So this is the last dimensionless number. And this is also very important in compressible fluid as I told. So here anytime if you come across Mach number, is a dimensionless number. So if the Mach number is equal to 1, we are going to tell it as sonic flow. Okay. Or any planes are flying with respect to Mach number 1 means it is flying at a speed of sound. So it is a sonic flow. If it is Mach number less than 1, or the planes are cannot fly more than 1 or less, can fly with less than 1, then it's called a subsonic flow. So now here we are talking about flow, means we are assuming the fluid is flowing, air is flowing, body is stagnant. If the body is flowing and liquid or the what is that? A fluid is stagnant, then we can call it as supersonic type of body. So whenever the Mach number is more than 1, okay, more than 1, with some given values, up to that we can call it a supersonic flow. If the Mach number is more than 1, means the body in the atmosphere or in the fluid or in the liquid, it is flowing more than the speed of sound. That is supersonic flow or hypersonic flow. It is very high number. If the Mach number is very high, then we call it as hypersonic flow. So later with respect to planes, we call it as supersonic jet or hypersonic jet with respect to bodies. So here applications are aerodynamic testings, missiles or jets, water hammer effects, the flow of gases exceeding the sound of velocity. In such cases, whenever we talk about velocities with respect to sound or more than sound or less than sound, then we are going to apply this method. So I hope all of you understood how to write the equation for the dimensionless numbers taking the different ratios. So later we need to remember what is Reynolds number definition. Definition means what is the ratio and what is its importance and its applications. Any doubts in this dimensionless numbers? All are listening to the class. All of you keep in mind to remember these all five dimensionless numbers. Suddenly, you can remember the Gauss number is taken. Sorry, all the dimensionless numbers in the fluid mechanics. This Reynolds number, Proust number, Rayleigh number, and Mach number. We need to take the ratio with respect to inertia force. The inertia force is common for all the dimensionless numbers in fluid mechanics. With respect to what ratio is taken, that defines the dimensionless number. And only Reynolds number is having or not having the square root. Only Reynolds number is not having square root. But remaining all dimensionless numbers are having the square root. If you take the ratio with respect to inertia force and viscous force, it's the Reynolds number. If you take the ratio with respect to inertia force and gravitational force under root, it is Proust number. If you take ratio under root, inertia force to the pressure force, the Euler's number. Then if you take the ratio under root with respect to inertia force to the surface tension force, that is called as Weber's number. Then last is Mach number, that is, if you take the ratio under root inertia force to the elastic force, then it is called Mach number. Okay. So these are the five dimensionless numbers we have seen in the dimensional analysis chapter. The last part is understanding what is model and prototype. Okay, so model is a small scale, like your toys, car, or a small games, what you play with small gadgets, which are scaled models or a replica. Okay, which will behave similarly as an actual model or as like a prototype. So that is called the replica of the actual structure of a machine, which will behave similar to the actual machine or actual structure. So before building any final actual model, everyone needs to save the money and save some time. Because once you build with lot of investment, and if any failure is there with the actual model or the prototype, then there will be huge loss of time as well as money. So before going for that actual implementation, okay, you need to check all the properties, all the conditions, all the working requirements, okay, with respect to the model, because model is costing very less. And after scaled model, you can invest very less amount. And time required to test these models is also very less because you can handle very easily. So in any experimentation, similarly your labs also. In your lab, if you see, many times you are going by models. Small model is taken and some small tests are done on that. Then you can increase the scales and you can tell for a big model what is the conditions. Okay. So they have written here, engineers always engage in the design of hydraulic structures, the dams, buildings, because here we are talking about fluid mechanics, so they have taken hydraulic structures. You can take aeronautical structures, aerostructures or aerospace devices or machines with respect to aerospace. Here we are talking about turbine and pump. You can take some other devices with respect to aeronautical applications. So before going for the actual systems to design, so they want to find out in advance on how the actual structure of the machine would behave when it is applied on the models. The model, we are also applying the conditions in the scale way only. So for example, if the discharge we want is 10 meter cube per second, for a scale model which is reduced to 10, I can take the discharge of 1 meter cube per second like that. The small discharge, I'll apply for the model and I'll check the behavior. So once the behavior is accepted or all the conditions are accepted with respect to model, then we'll go for the actual model building, that is called as prototype. The actual structure or a machine is called as a prototype. So for this purpose, they need to experiment, design, and you have to check for the all behavior of the models. And then they'll scale up the model. Okay, so it is not necessary that model should be smaller than a prototype, because many times what happens, I'm telling here for a small discharge I'll go by model, large discharge or for actual discharge I'll go by a prototype. It's not like that. Sometimes what happens, a small miniature product also you have to prepare. In such condition also, the model may be big one so that everyone can see and check the behavior. Then they will go for the microstructures or a small structures. That's it. So model is a scaled model. That's all. Whether it is a small scale or a big scale depends on the applications. Okay. So now analyzing this model is what the study of model of actual structure of the machine is called model analysis. Means the actual structure of the machine, whatever is required, are the same behavior, same properties, same conditions, you have to build a model also. Like let's say a doll. Okay. So on that, what you are doing, you are checking all the dimensions, proper height, okay, then different dimensions we are considering and we are preparing a doll or a model. On that, it should also look similarly, also behave similar to the actual model. So it is actually an experimental method of finding solutions for a complex flow problem. So before going to a complex flow problem or combination of different flow properties, in the model, you can check one by one and later you can go by combined effects. So once the combined effects are valuable or can be accepted with the model, then you go for building a big model that is called a prototype or small model which is required small model, then you can call it as prototype. Prototype is a actual machine which is in application. Model is not in application. Model is just made a replica of the actual structure and some experiment is done on the model. Okay, so what is the advantage of this? As I told, the performance of hydraulic structure on any machine can be easily predicted in advance. Okay, by spending less investment and it is also more economical and convenient because design, construction, operation of the model can be easily varied in any time if required because it is very small and maybe sometimes for a model we can go for different conditions and only in a small given space we can run the experiments. Okay, so whatever the defects are observed in the model, those defects can be overcome directly in the actual model, or else you can change the model itself and can again run the machine and check the efficiency and the suitability. Then you can go for the actual model building. So last part in this syllabus is comparing all these three types of similarities. So that similarity is called the similitude here. In the dimensional analysis, we are going to find as similitude. The similitude is defined as the similarity between model and the prototype in every aspect. What are those different aspects of this similarities are? One is the geometrical similarity should be geometrically same. Okay, whether it is a big one or small one, geometrically the dimension should be same. Next is the kinematic similarities or the flow similarities. Whatever I told, velocity, discharge, or acceleration, or angular velocity, both for model as well as actual prototype, both should be similar. I'm not telling same, it should be similar. If I tell I can ride a bike up to 80 kilometers per hour, then model I can build, it can run up to 40 kilometers per hour. So for that condition, what is the application for there? Same thing should be applicable for the other prototype also. So maybe speed may be same, can be maintained, but with the small geometries. Similarly, dynamic properties, which are nothing but the fluid properties. The property of the fluid also should be same with this property. So which means that model and prototype have similar properties and model and prototype are completely similar in all these three aspects. Then that type of system is called as a similitude. So whatever the lab in the lab you are taking a model and analyzing it, that is nothing but a similitude. It is having a similar properties. The geometrical properties you can just recall diameters how here. Model may be first one, this may be actual model, smaller or bigger. I can call this box, small box as a model, and this big box as a replica or a prototype. Okay, so P shows here BP, M shows model. Once you take those ratios, they are called as scale ratio or the length ratio, CLR. So this ratio may be with respect to volume, area, or length, whatever. Similarly, kinematic similarities. See here, now prototype and the model, these are having only geometrical difference. But how the flow properties are taking place about this body should be similar to the model also. Okay, so if this body or the model is behaving properly with these flow properties, then I can assume for the actual prototype also the kinematic similarity will be achieved. Then I'm going to build the bit model. Okay, so this is called as existing between two prototype or model. If the ratio of velocity and acceleration at the corresponding points at point A, B, the kinematic similarities like velocity acceleration on this side at the corresponding points are same. Okay, so here it should be same, but in the geometry it may not be same. Ratio may be same. Ratio for all length, volume, and area it may be same. So this ratio is called as again VR, called the replica of the ratio between prototype to model ratio. Acceleration ratio is called as VR. So this you can just read and understand. The big challenge. The geometrical similarity is necessary condition for kinematic similarity. If both are achieved, then you have to go for testing dynamic similarities. Okay. So in dynamic similarity, what we are doing, we are checking now all the fluid properties on this body, how they are changing. Also, we are checking the dimensionless numbers, like Reynolds number for the model. For the model, you can also checking the Proud number or Mach number. Because if you compare, if I replace this car with the aeroplane, you can check with the Mach number also. If the Mach number is working properly with the model, then you can go for the actual model. Okay, so all those fluid properties we are comparing here. So inertia force is compared with prototype and model. Then viscous force is compared with the prototype and model. Then that is called as force ratios. All these fluid properties of the fluid ratios if you compare, then it becomes under dynamic similarity. So this should be also same. So both geometric, kinematic, and dynamic, all these properties should be similar. Okay. Only geometry may be smaller or bigger to reduce the cost or reduce the time or make it economical. You can tell the geometrical property is different. But kinematic and dynamic property should be same for the prototype as well as model. So recently I heard that I think Rafael model. So they were doing in news that the complete model analysis, testing, everything is done only on the computer basis. Okay, directly they have made a prototype without testing in the model also. Okay, so only using the software, they have made a actual environmental setup or actual environmental system. Under that, they have tested every properties like similitude and other things. They find using that in the software, they have tested everything, even with electronic gadgets, body, aerodynamics, everything. Then directly they have made a prototype itself, not even a model. How much it is true, I also don't know. But news I heard that everything is done after software. They have directly come to make the prototype itself, and that prototype is successful. So that you just check in the news how they have made it without making a model. Okay, so this distorted and undistorted model is not there in the syllabus, I feel. Okay. Or can read these types of models later stage. Can take it for a self-study part. So this completes our dimensional analysis chapter. Okay. The time is 11:45. So first of all, I want to request you go through that Buckingham pi theorem and Rayleigh's method. Practice some other problems from the books so that you will get some confidence and grip on the problem solutions. Okay. Still any doubts are there, you can take doubts later. That's clear. And dimensionless number, similitude, everything is the theoretical part. You have to just read and understand the concept behind this making model and prototype, how they are important. Also, you can remember one more thing. The prototype is not made directly because we need to reduce the this accidents out. Real time, if you go by any device without checking its properties or proper processes, then what will happen? The actual model, without any knowledge, you may have some big disasters. Because if you go by some plain or chip testing, it may disaster or we may have many accidents also. So to reduce that, we have to go by model. Only in a given small experimental setup or a given small area, you can test it. You can have small accidents. Then later we can reduce the big accidents. So that short table is also there here in this PPT. I will club these two PPTs and I will send you the classroom. Okay. I'll stop the class here. Next Monday we'll start with the fifth module.